We're going to get started with a little warm-up. I know that they've closed the doors. I don't know if that's good or bad. And I'm kind of curious about why those doors are not exits. In case, a lot of times I speak a lot, but I got to tell you right now, the lights are here, and I'm like terrified. No matter how many times you do this, when you see a bunch of people sitting there, especially engineers, you know what, you're all just sitting there. Just say something wrong. Just say one thing wrong, and we will be all over you. Or just say something marketing related. But before I actually start my content, I have a special PowerPoint slide that I made up. I want to thank the conference organizers for scheduling me on the last day when it looks like I showed up this morning and everything was packed and gone. Where all the exhibits are, and I go, is this right or not? But I have so I've been keeping track of some observations here. Hold on a second. So yeah, here's some of my personal memories so far of the Build conference. Now, it's not over yet, of course, but I want you to think back. So the first thing that struck my, oh yeah, by the way, AV people, do not record this and post it on Channel 9. So the first thing I noticed when I showed up, I thought I was misreading my schedule wrong. Keynote, 3 hours. And I go, surely there's something wrong here. They're going to break it up, or there's some special thing in mind. But no. So, somewhere, that some brilliant marketing person go, our keynote. Wait a minute, this is Build 2014. Let's make it 3 times as good. And nobody is going to say, wait a minute, there's people that are going to have to sit there in a crappy chair for 3 hours, I don't know what they were thinking about. Okay, after the keynotes, but actually the content was pretty good. Here's one thing that I couldn't put on the slide because for sure I'd get fired. But I noticed that everybody up there had this vaguely hipster look. You know what I mean? Hair over my face, I did not see one guy up there, even these most senior executives, they're all wearing tennis shoes, like Converse, or something like that. Well, I'm sorry. My pants are from Sears, they're Dockers. My shirt is from Sears, it's a Land's End. My underwear comes from Fred Meyer. I don't know if you guys know Fred Meyer. It's a local Pacific Northwest store, but it's cheap stuff, okay? So, I'm sorry, but you're not going to get a very hipster kind of account here. That, like I said, I couldn't really put that in because those are all my bosses. Let's turn our attention to the meals. I have some theories here. The first thing was, okay, so, I speak at a lot of conferences, and the meals are a pretty big deal for me. But apparently, the same marketing person who was suggesting the 3-hour keynote goes, I know how we can save maybe $500 at this conference. Need I say any more? You show up and there's a bowl full of eggs. Now at first, sorry, I'm getting a little bit nervous, getting a little bit carried away here. I'm going to leave the eggs alone. But then lunch rolled around, and I decided, maybe this was a first day thing. But then I noticed at lunch there seemed to be this vaguely burrito trend. You know what I mean? And at most of the places I speak, there's like banquets with actual real food. But I was sitting down on the first day, and I was sitting with a bunch of fairly crusty, cranky engineers. I know that's redundant. They're engineers. And they'd been to several at the lunch table, and they'd been to several of these conferences before. And they were pretty harsh about the food. They go, man, this food is the worst. And I was, being the good corporate, I had my Microsoft logo on and stuff like that. Of course, I felt obliged to defend the whole thing. And I go, well, these burritos aren't that bad. It could be worse. So I decided to prove that, in fact, it could be worse, but that was kind of an extreme thing. Okay, now my final, or my next to last observation, by the way, I've noticed I'm using up the entire time, so apparently, no, we will get to neural networks pretty soon. But, seriously, the main reason why we come to conferences is, I think, for a sense of energy, and to see a vision of what Microsoft is going to do. Because, the reality is we love what we do. I mean, I can say that, not knowing anything about you. But part of the fun, or the deal of coming to these conferences, is recharging your psychic energy so that when you go back, you're ready to work. And so at most of the conferences I speak, there's a lot of pizzazz. For instance, here is a photo of an actual conference I was at in Las Vegas some time ago. This is a Microsoft conference. Notice band playing, people dancing, open bar, and stuff like that. Well, apparently, that same marketing person had a different idea of the pizzazz for this event. So this apparently is sort of like the side event highlights here, the meditation room and the mother's room, and not exactly my idea of high energy. Now, finally, I didn't know, I had to set the context here. This is a social thing that, does anyone know the name of this movie? Treasure of Sierra Madre, several people. It's an old movie, but you all know the line, I presume. Maybe you don't, because I notice we have lots of people from non-English speaking countries like Australia and Canada. And so, there's a famous movie with a famous line, so I felt really out of place here. Oh, in fact, just to show you, this is, just sort of like to show you my insane PowerPoint skills.
You're the police, where are your badges? Badges? We ain't got no badges. We don't need no badges. I don't have to show you any stinking badges.
Okay, now what does this have to do? Well, I'm reading I'm watching all these talks and stuff like that. I'm feeling like totally out of sync. My stuff is going to be, my presentation is going to be about actual code. Okay, no, I'm sorry about that. So, I'm sorry, for this talk at least, we don't need no stinking JavaScript or CSS or any of that stuff. Okay. Okay, that ends my little pre-song and dance, get us warmed up. So, yeah, and presumably, if any of my bosses see this, I'll be sharpening up my resume immediately after the event, and if you have any openings in your organization, let me know. Okay, oops, wrong one. Get rid of that. Okay, what I'm going to do now is, can you still hear me? It sounded like I might have, the powers that be, shut me off somehow. What I always like to do is sort of walk through, you notice I've got PowerPoint here. I'm going to walk through the slides to give you sort of a preview of what you're going to see. I just like to do that, so give you sort of like a cognitive map or whatever you want to call it. Because there's nothing worse than seeing like okay, well here I'm just going to walk through it, okay? So I'm going to show you the agenda and like the danger thing, and why those guys are standing in the back of the room is because like I always stand in the back of the room at the beginning of a talk. If I see the agenda and it has like 48 items, you're going, oh dude, you do the math, there's just not enough time for that. So we've got about 12 slides. I'm going to explain what a neural network is to give context. I expect that this is sort of a repeat from last year's talk. Again, this is more of the same. The emphasis here is going to be on things that are sort of new in the world of neural networks over the last 18 to 24 months. And when I say new, not necessarily research new, but things that are filtering into the developer community. And one of these is the use of backpropagation. It's related to deep neural networks. We'll talk about that. This other thing is called mean cross-entropy error. This is a low-level thing, but I'll explain what it is and why you should know what it is and what the current thoughts on it are. Model overfitting still is the biggest deal in neural networks, and I'm going to describe this technique that was first published in 2012 called Dropout that really has had a big impact on a lot of areas. It's really simple. I'll explain it. Then I'm going to do 3 demos. An actual, a console application. I don't even like, to go up to WinForms. WinForms is a little bit too fancy for me. I'll show you a canned application. Then I'll discuss this briefly. A vision for the future. This is sort of like something that I think you'll get really excited about. This is the most exciting thing for me. And then this is going to be my answer to Cortana. It's called Cortina, and you'll see a demo there. Then the resources here, and I guess this gives me an opportunity to say what the goal of this is. The goal is for you to see 3 demos. And the resources here will allow you to replicate any of those 3 demos. Either run the tool that I show you, or actually download raw source code. I'm sorry, it's not in a zip file or anything else. You're going to have to copy and paste it into Notepad and run any of the demos. Then, if we're really lucky, either thunderous applause or not. And I will say before I forget, because I know that I get all wrapped up in my talk at the end here. This talk, the organizers didn't really want to have this talk. I really had to push to say, let's have something forward-looking about machine learning and neural networks. And the general thought is, people aren't ready for that. It's too advanced or it's too esoteric. Well, I think differently. I think that, it's really fascinating. It's what drives me, larger than a big tile that you can swipe with your finger. In either direction. So I encourage you to fill out the sessions with particular emphasis, and I'll be honest here. If you like the talk, say so that there will be more talks at other events like this or your local talks that Microsoft organizes. And if you didn't like it, say so too, because there's only about 130 speaking slots, and they're very valuable, and we want to deliver the most useful information to you. Then, I've always wondered at the very end, what is in that super fine print down there, but I don't think we'll have enough time to get there. Okay, so here's the talk. My name is James McCaffrey. I work at Microsoft Research in what's called the Advanced Development Team. Typically, what we do is we work across Microsoft with different product groups, and I'm sort of a hybrid, and many of us are, where we sort of understand research. In other words, I've got a PhD in applied mathematics, but everybody else at Microsoft Research is a better mathematician than me. And I develop code, but everybody else, the developers are all better than me, but I'm sort of good in between. In other words, I can read the research papers and understand all the Greek letters and translate it into code and act as an interface. So kind of thing's what I do. I may have an interesting project to show you. It wasn't on the slide if we have time. I'm also the senior contributing editor for MSDN Magazine that maybe many of you read. I've worked there for about the last 12 to 14 years. And that means I just sort of review article proposals and things like that. Okay, so there's my agenda. Well, you already saw it, so no need to go over that again. So what is a neural network? I think, everybody thinks in different ways, but for me, one of the hardest problems in my day-to-day work is knowing well, I'll just cut to the chase. With regards to a neural network, the hardest problem is knowing, okay, you have this problem, can a neural network solve it? I just got an email the other day from some guy, a reader, MSDN Magazine reader, and he was talking about laying things out on a page. Imagine a bunch of things out on the page with arrows pointing to them, and he wanted to have some automated system that would lay them out in such a way that the arrows wouldn't cross over a box or something like that. And I thought, well, no, that's not a good problem for solving a neural network, or by use of the neural network. For me, if you can somehow transform the problem into an Excel spreadsheet where you have data like that, then a neural network is one of the ways to solve this. It's called, classification in fancy terms. So in particular here, you have some training data. Neural networks aren't magic. In this particular scenario, we're trying to predict the political party affiliation of a person based on their age, their annual income, their education, and their gender. So I mean, that makes pretty much sense, right? So in this case, we're trying to predict something that's called a classification, where the class can be Democrat, Republican, or other. But neural networks can predict any one of those columns. So we could use the other columns to predict the person's age, or use the other columns to predict their income, and so on, okay? Now, in technical terms, they all have slightly different meaning. Like, if you're predicting a numeric value, it's called regression, and if you're predicting a label, it's called classification. And I guess that also reminds me that the vocabulary in the field is very chaotic, and it makes it very difficult to understand what's going on. So in this case, we have some data. It's totally faked. And our goal is to predict the political party affiliation of a 35-year-old male who makes $49,000 a year and has a high education level. Now, before I go on to the next slide, notice that the education could be one of 3 values, and the sex can be one of 2 values, even in San Francisco, apparently. I don't even know what that means, but you always have to throw in some slam at San Francisco, from living anywhere else. And so education can be one of 3, sex can be one of 2, and the political party affiliation can be one of 3 possible results. And down at the bottom, independent variables, predictors, attributes, features, X values, again pointing out that there's chaos in the field because different people in different fields use different vocabulary terms, which makes it very difficult for software engineers who actually want to write a program that does something. So here is the picture that relates to that previous slide. Now, the first thing you're going to see if you type in neural networks into your search engine, never mind. You're going to see that box with all the crisscross lines. Now, I remember early on, many years ago, seeing this, I go, okay, I see a box with a bunch of lines on it. I don't get it. Why is that a neural network? What does it really mean? But what's important is the box with the lines on it is just the processing, okay? You can think of, if you look at the overall thing, a neural network is nothing more than a fancy math equation. Here we've got 1, 2, 3, 4, 5 numeric inputs. So if it's a math equation, it accepts numeric inputs and it outputs numeric values. So that's one of the key things, is that because it only understands numbers, or can only work directly with numbers, you have to translate non-numeric values into numbers. So the age and income. This is an example of what's called data normalization, where we're sort of scaling them. And the idea is pretty simple. If you didn't scale them, in theory, things would work, in theory. But in reality, they don't work. If you scale them, you want the numbers to all be relatively the same, typically, somewhere between -10 and +10. So does that make sense? And there's 2 ways to normalize data. Does anybody even know? I mean, see, here's where, using neural networks, this is really the hard part. Once I get to the box with the lines, that part's pretty easy. But understanding, why are there 2 different ways to normalize data? Well, it turns out there are 2 different ways. It doesn't really matter too much which one you choose. Now, the education, we said, could be low, medium, or high. What's odd about that? Okay, this part's encoding. Encoding means translating a label to a value. What seems a little bit odd about that encoding? Yeah, okay, so high goes to, or education goes to 2 values. When we said that education could be one of low, medium, or high, right? So that seems a little bit odd, but that's just one of the tricks of the trade. This is called 1 of n-1 effects encoding, and that's the way it works. The bottom line is, we could talk hours about this, which would sort of be like a boring keynote, but instead, all I'll say is, if you have 3 things, it goes to 0, 1, 1, 0, or -1, -1. And that sounds a little bit odd, but once you know that trick, you're good to go. Now, it's sort of close. Sex, which we knew could be, male or female, goes to only 1 box. And again, you can sort of guess now. If male is -1, what would female be? 1, as opposed to you would probably incorrectly guess to encode male and female as 0 and 1, right? Well, it turns out that would, in theory, work, but this works much better. So anyway, the first part, and this is one of the annoying parts of dealing with neural networks, is this data encoding and normalization. Then you feed it into what is essentially a black box, and it's just an equation. It's just a fancy math equation. Like, equations like y equals x squared plus 3. It's really just a sophisticated version of that. And now, can anybody interpret the output? Our outputs were Democrat, Republican, or Independent. Now, you might have, if you were thinking too hard, you might have guessed that the outputs would only have 2 boxes, right? Because if the inputs only have, 3, no, it doesn't work that way. But believe me, in this one slide, I've told you everything you need to know to be very effective with actually using neural networks. But can anybody interpret what those 3 values mean? Likelihood, probability, that's correct. Now, they're not really probabilities, but you can interpret them to mean the probability of Democrat, the probability of Republican, and the probability of other, and then this is just called winner takes all. The highest value is the one that you make the prediction on. So that part's pretty easy, and this next slide just shows the internal. Now, one of the things that I remember when I was first learning about neural networks is I kept running across this term called the perceptron. Now, the perceptron is just the basic circle in the other diagram. And here's sort of a close-up where you've got nodes feeding into other nodes. You can see this is like a little subset of the other picture. And this shows you how to compute an output. It's really easy. So if 0.10 is the input, either the input into the system to begin with or one of those intermediate inputs, and the W's represent weights, okay? And weights are just constants, typically some small number between -10 and +10. So you can see up there in the upper right-hand corner, you just, I don't even know how to describe, I could describe it as a dot product or something like that, but you just multiply input times constant plus input times constant plus input times constant. And from the developer's point of view, it's sum plus equals x times y kind of thing. Then the little b, anyway, so you add them up and you get 1.2. Then the little b is called the bias. The bias is an extra value that you add in. It's just an extra constant, and it turns out it's hugely important. There's some things in neural networks where you go, okay, people, I'd be inclined to go, and the bias is just another value, but I can't state how important this thing is. The bias is hugely important to how these things work and how everything you read about it, you have to be very careful of this bias term. And you can see in the upper right-hand corner, you just add the bias term to that sum of products. Then you apply some activation function. Now, if you didn't have the activation function, all you've got is plain algebra, okay? And there's no magic. But applying the activation function is the secret of why neural networks work. And I'll explain activation in a second. So you just supply some function. Again, from a developer's point of view, just think of it as a function, accepts a double and spits out a double. That's all you need to know. And so there's our local output, 0.73, and that gets emitted to the next phase in the network. So pretty easy. Now, in the lower right-hand corner, this bias thing, I think, it's so hard because, I've been working with neural networks for years and years and years. And I am so tempted to just blast over the bias value, which is this thing in the lower right-hand corner. But I remember when I was first learning about this bias thing absolutely gave me fits. It was one of those, whenever you're trying to learn something, there always seems to be a few things that aren't all that important, but they're hugely, just huge stumbling blocks. Well, the bias was a huge stumbling block for me, and presumably it might be for you. So it says, most neural network literature treats the bias as a special weight that has a dummy input. Okay, so just watch what happens here. So I'm going to replace, again, I harnessed my PowerPoint animation skills here, and watch the b equals 2.0, which is just a constant, is replaced by a new dummy input node that has value 1.0 and a new weight that has the same value. So do you see, if you just followed the pattern now, input times weight plus input times weight, and then you get 1.0 times the bias, and you're right back where you started from. So, well, what's the point? The reason why, okay, so in other words, almost everybody does this. So this creates havoc for trying to read the literature, because you're never quite sure if the bias is really a bias or the bias is a special extra weight that has this special dummy value. And are the dummy, it'll drive you nuts, and you got to be really careful. And there's no way to say except it's just a stumbling block. You have to read very carefully. Okay, now the activation functions. You'll read about these all the time, and I won't say too much about them, except those are the 4 that you need to know about. There's other kinds, and I would say in the last, I don't know exactly how many years, but the hyperbolic, never mind. In the early days of neural network research, everybody used the logistic sigmoid function for everything, because it was very, easy to analyze and had nice calculus derivatives and blah, 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 blah. But the hyperbolic tangent is what I use when I want things to work, and softmax is what I want to use when I want things to work. Okay? So I'll just say that there's some not controversy there, but you'll get conflicting opinions on that. Okay, now, this is related to deep neural networks. Has anybody heard that term? Raise your hand if you've even heard the term deep neural networks. It looks like about a third of the audience. Deep neural networks are the current hot topic in machine learning research. Deep neural networks. So, what is a deep neural? Does anyone think they know what a deep neural network is? Well, I was going to say that that's kind of a trick question, because there isn't a standard definition, exactly what it means. But one of many possible interpretations of a deep neural network is in the blue box here, we have an input layer. Those are the inputs. Then the hidden layer is the processing, where the multiplication and activation goes on, and likewise the output. So a deep neural network is one that just has multiple hidden layers. Okay? So what do you suppose that might do? What would the point be of having? I mean, just guessing generically, can anyone think? I mean, like, why would you want to have more than one hidden node? I'm sorry? More randomness. That's a pretty reasonable and close answer. Yeah? Anybody else? I'm sorry? More abstraction. That is also correct, although most of us wouldn't know what that means. Well, okay, so wait a minute. Someone back there said more weights to train. Okay, so that's a downside. See, training is the process of, I showed you in the slide where the weights are. The whole deal about neural networks is where do those weights come from? You have to find the weights that make the neural network predict the training data. Okay, so more connections is like more abstraction. It makes it more like the human brain kind of thing. You figure if it's more complicated, it can solve more complicated problems. And that's more or less true. There's some asterisks to that, but deep neural networks, now, and it's obvious, people have thought about deep neural networks for the longest time, but the basic idea here is that until recently, this reminds me so much of chess, okay? Does anyone remember chess programs in the 1990s or something like that? Or maybe 1980s, Chessmaster 2000 and stuff like that on your, your clunky little Commodore machine? Well, now, true or false, now the best computer programs can beat the best human players. True or false? True, raise your hand. False, raise your hand. Well, it's true. The best computer programs can now destroy the best Garry Kasparov or Magnus Carlsen or whoever. Well, what was the big breakthrough in these chess-playing programs? Well, I'll tell you, it was just raw processing power. It wasn't any fancy magic algorithm heuristic. It was just butt-crunching numbers, I don't even know. I just made that up. I feel, sometimes I feel like I'm trying to be a Seinfeld or something like that. I just throw out something, and You know, it's halfway out of my mouth, I go, what am I even saying? I don't know. So deep neural networks have been around for a long time, and they haven't really been effective until recently because it just requires lots of number crunching power. So a deep neural network just has multiple layers. And so the idea of adding in more layers, it is going to greatly increase the number of weights you have to find. In fact, you know, I'm kind of a math guy, so I always have to throw in an equation just to show my math colleagues, yeah, I can throw in an equation there. The number of weights and bias values that you have to determine is A times B plus B times C plus blah, 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 blah. And there's an example down there. But for some problems, like vision recognition, okay, imagine instead of, you know, the Excel diagram, vision recognition, imagine millions of pixels, you know, trying to predict if something like that. So if you've got millions of input nodes, you're going to have hundreds or billions of weights to determine. So that's really the hard part. Now, backpropagation is the original. This is another thing I remember when I was learning about neural networks. I remember that every time, backpropagation is so pervasive through the field of neural networks that if you don't really know a whole lot about it, if you're just getting started, you think backpropagation is neural networks. But it's not. Backpropagation is one of 3 primary algorithms used to train the neural network, to find those weights and bias values. Now, who can tell me why backpropagation, it's a cheat, I'm tricking you. Why is backpropagation by far the most commonly used algorithm? I'd say 99% of all neural networks use backpropagation. Does anyone know why? Yeah, what do you say? I'm sorry? Yes, but I'm going to be even harsher than that. What do you say? Okay, that's kind of true. I'll give you the real reason that I'm just making up, in my opinion. And that is, if you look up backpropagation, you will see one of the most beautiful mathematical proofs ever. You can find this over and over again. It's repeated time and time again, where they're taking derivatives of this and moving things around and rearranging terms. And it is one of the most beautiful math proofs ever. Well, if you're in research, how do you get evaluated on how well you're doing your job? You publish a paper, correct. And you can only, believe me, I grew up in the academic world. I was a university professor. In fact, where's my student here from? Isn't that you, the Bramwell? No, sorry. Oh, there he is. No, I can prove. When was I your teacher, roughly? Early 90s. Okay, it was about 25 years ago. Back when I had a real job. And, oh yeah, back to research, Simon research. You only publish research if you have mathematical foundations of this. And genetic algorithms and particle swarm optimization are considered sort of black magic and kind of like second-class citizens in the research world because you can't prove cool theorems like you can with calculus and backpropagation. Now, it's my pure opinion that one of the keys to success moving forward with genetic algorithms as processing power becomes more abundant is the use of particle swarm optimization in conjunction with deep neural networks. You know, multiple layers. But that's just an opinion, I can't back that up. Error and accuracy. One of the things that I gave a very similar talk to this last year, and between then and now, I got lots of questions about something called cross-entropy error. So think about training the network, okay? You've got this network, and you're trying to find the weights and bias values. Could you just randomly try weights and bias values? Just randomly try it. Would that, I mean, could you do that? Yeah, but what would be the problem? Yeah, it just takes forever. There's too many of them, and there's too many possible numbers between negative infinity and positive infinity to try. So when you're training, you have to have some way of knowing how good your weights and bias values are. In other words, you have to measure the error. And there's two ways to measure error. Usually, the classic way is called mean squared error. So look at that top thing. We have computed outputs in the very upper left-hand corner, 0.1, 0.9, and 0.0. And we're trying to get 0, 1, 0. That might correspond to, like, the training data says the output, the real output is a Republican. 0, 1, 0 is Republican. And the computed outputs were 10% Democrat, 90% Republican, 0% independent. So is that good? Yeah, that's the correct thing because 0.90% Republican, and it is Republican, so we're good there. So you compute the error of those three things is just, you know, you subtract one from the other, square them, add them up, divide, you know, and you get the idea, you know, if not the details. And so that's the first way. Well, there's this alternative called cross-entropy error. Now, without going into details, if you look down at A, just look at that equation. Even if you don't even remember, if you were like did what I did in high school, I was a terrible student. I was constantly in detention because I would always miss my afternoon classes after lunch, including all my algebra. But even if you don't remember what a ln is, just look at that equation. What looks a little bit odd about it? It's not the way a developer would probably write that equation. Anyone see something kind of weird? Yeah, you're multiplying by zeros, okay? See, as developers, we'd go, if this is 0, then continue or, you know, break or something like that. But there's reasons why you multiply by 0. But in short, the cross-entropy error is taking into account only the one that matters, okay? Now, that's the theory of it all, and there's some research evidence that's not conclusive that cross-entropy error is better, okay? And that's sort of this notion has been around since 1998, but only now are people starting to sort of glom onto that, I think. So I have, you know, a lot of this, you're going, oh man, there's too much details here. I've got all the references or the resources I will point to. Okay, now model overfitting. Model overfitting is this huge problem. And so the roulette example, red, red, black, you're trying to train a neural network to predict roulette. By the way, do you think it would be possible to predict, let's say, the winner of the Super Bowl or the winner of the NCAA tournament using neural networks? The answer is yes and no. It's kind of a tricky issue. But anyway, suppose that's called a time series thing where you're going, things are unfolding over time. Red, red, black, red, red, black, red, red, black, red, red, blank. Any neural network in the universe, no matter how you design it, no matter how you trained it, would predict one thing. It would say absolutely, positively, the answer is black, because it sees the pattern. So that's overfitting. Overfitting is finding an equation that fits the training data really good, but fails on, the first time you use it, when it counts, it fails. So there's a lot of techniques. I'd say model overfitting is the hardest problem in dealing with neural networks. And there's a bunch of ways to deal with it, including the one that's the subject of my next slide here. This is called dropout training. This was the idea is kind of crazy. So here's a neural network that's got 3 inputs, 4 processing nodes. By the way, a question that, again, because I work with these things all the time, the obvious question I had in the beginning was, how do you know how many hidden nodes you're supposed to have? The input nodes are determined by your data. The output nodes are determined by your data. The hidden nodes is a guess. Basically, you just try different numbers of input nodes and see which ones work the best. But here we've got, this is a dummy neural network. The idea of dropout training seems really bizarre at first. You randomly pick on each, okay, so here we've got a training data where the inputs are 1, 3, and 5. We randomly pick 2 of the processing nodes, any 2, or 50% of them, which is 2 in this case, and we drop them out of the picture, and we don't drop them physically, but we drop them, programmatically, where when we're going through the for loop and we hit that, that index i equals 3 or whatever it is, you just, skip over it. So now we have sort of like a neural network that's been culled or, pruned down a bit. Then you generate your outputs, and then you try to improve your weights. Then here comes the next input. 2, 4, and 6. This is another piece of training data. You select 2 more randomly and drop them. And the process goes on and on. Now, at first glance, this seems to make no sense. Or at least it didn't make sense to me. But there's a couple reasons why it does make sense. And I'll just leave it that it's a really fascinating thing, and it's currently, neural networks have been around for a long time, and there's been all kinds of techniques tried, but I'm a pretty much of a believer in this dropout. It's easy to implement, and it dramatically improves the neural networks that I work with. And I can give you, actually, I'll say this now because it's not in the resources slide. I've been doing I also work for Visual Studio Magazine. Do anybody ever read that? It's an online-only magazine, used to be. So I've been doing a series of neural network things that dive into low-level details. And there's one on dropout coming up next month. So Visual Studio Magazine, you can read about all of these things in great detail. Okay, now here I'm going to finish up my talk with, we've got 17 minutes left at most. I wanted to get done well before an hour. I don't even like to listen to anyone for an hour. I'm going to do 3 quick demos, at least, and maybe a 4th. So here is a neural network demo that I will point you to the source code to. So it's Visual Studio. We talked earlier about, is anybody in here a user experience engineer? I'm going to make fun of you all right now. For me, user experience means typing something into the shell and hitting enter key, okay? That's my user experience. And for UI design, my height of UI design is when I change the color of my shell. That's like ultimate in fancy for me. So I have my very fancy blue with white font there. This is the most famous demo in all of neural networks, so that's one of the reasons I'm showing it. It's called the Iris data set. So the raw data, this is an actual raw data, I forget what it was, 1930-something. A researcher named Fisher actually found iris, 3 different species, and he got a little whatever measuring thing they use and measured them. So I don't know what the units are, but the first one is some species called Iris setosa, and it's the petal and sepal. I worked with these things for like 20 years before I ever actually bothered to look up what a sepal is. The petal is like the flowery part, but the sepal, apparently, I've never really looked at flowers very closely, but there's this like green thing that's kind of like half leaf and half petal. Raise your hand if you knew that. Get out. We don't like your kind. But anyway, so I measured the little green thing. Yeah, for me, like flowers, The only time I notice them is like, crap, it's February 13th, dang it. So those are the actual data. There's 100, and the true data set consists of 150. So that's what the raw data looks like. And this is, I'm reading this. Actually, I've got this hard-coded. So the first thing we do is you create a training and test set. With the 150, we could train on all 150 of them, but it's tradition to only use part of it. And hold out, it's sometimes called a holdout set, the remaining, typically 20% or 10 or 30%, so that we can evaluate. We train on the training set. But then, we go, well, is it any good or not? Then we run it on the leftover set to get an estimate of how well we do on a flower we've never seen before, an actual flower that wasn't part of the set at all. So what just happened in this part of the demo? The raw data to training data, I'm actually storing it inside a matrix. But what happened to it? Okay, I'm not talking until someone says an answer. No, what happened to it? Well, there's more. So what transformation happened there? Well, okay, so actually, it's not obvious at all. Oh, I take it back. Oh, I thought I normalized it. Or did I? Did I? I'm not sure if I normalized it or not, but at least I encoded the output, okay? In other words, the setosa is 0, 0, 1, and so forth. Okay? Oh, now I normalize it. Okay. So no wonder. And I normalize it and then I'm creating it. What does that mean in terms of, as a developer? Creating the neural network. What did I just call? It's one line. The constructor. I called the constructor. And there was the training. Now, this training was super speedy because the data was small. In a real-life scenario with thousands or tens of thousands or 100,000 of data items, training time is a huge problem. It can take hours or days or even more. Training is complete, and I spit out the weights and biases. Those were the best ones found by the algorithm. It used backpropagation, and it was on the 30 items, it got 28 out of 30 right on the training. And then on the test data, it did not quite as good, which is normal. And so this 93% would be, if we were now given a flower we'd never seen before and threw it into using those weights, we'd bet or we'd guess that we have a 93% chance of getting it right. So it's really pretty easy, I think. Okay, and I'll point you to that source code. See, because for me, it's like, I don't know. I mean, I could sit through any of this stuff, And if I don't see the demo code, I could sit through my own talk, and I'd leave, and I still wouldn't be any better off, because it's just blah, 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 blah. The only way I really understand is if I can see the code, run the code, and change the code, because that's how we all learn, right? It's not like we magically know how to do something. Every new technology you learn, you start with an example, and what I've tried to do is design this example that's just right, not too much, not too little. Okay, 2 more quick demos, then we're out of here. Actually, I'm going to cut to the chase. Here is my answer to Cortana. Now, speech recognition is something that I've been thinking about a lot lately for a lot of reasons. And did you all see the Cortana demo? I thought it was pretty cool. Sorry. So here's my answer because, again, I saw that demo, and I was absolutely close. I go, what's going on? I mean, how did that work? Is it magic? Are there a bunch of people there? I mean, was it faked? Sometimes at these demos they have the puppet masters who are sitting behind, the little microphone and stuff like that. Okay, so here is my little demo. We'll see. And this is a live demo, so I'm going to start it. Notice, console application. Hold on, let's show you the main. Main, see that? If I can see main, I'm usually happy.
I am awake.
Hello.
Cortina acknowledges your presence, insignificant human.
Okay. What is 1 plus 2?
1 and 2 is 3.
Cool. What is 2 plus 3?
2 and 3 is a fatal calm exception. Just joking.
Ah. Very funny, Cortana. Goodbye.
Farewell.
Klaatu, Brata, Nikto. Anyone know that reference? Klaatu, Brata, Nikto? That's famous. Okay, yeah, you have to be old and crusty like me. Anyway, so now, for me, this is speech recognition, not talking to some stupid phone. This is the truth. I can't tell you that. So here's the whole program. Look at the whole program. You can tell by the slider. And I actually even put in some comments, which I never do in my own code. That bulks up. But I'll point you to this demo too, and this is the canonical example. I went around in circles trying to get this thing to work. It took me months just to figure out what I had to install to, on my system. I mean, the documentation was horrible. So I tell you exactly how to do that. Okay. Now let's finish up. Oh, great, I shut my PowerPoint slide down. Here. Let's see. Hello, where'd it go? Oh, here it is. Okay. Where are we? So let me sort of summarize and say, sitting here in the chair, currently today you have 3 options if you want to work with neural networks. Number 1 is to write your own from scratch, okay? And that's pretty daunting, not because of the coding skill required, but because of all the background knowledge about how you encode and stuff like that. But it is possible. There's plenty of people, some of my snobby research colleagues, not at Microsoft, some of my external research colleagues, say, nah, you know, the normal developer community couldn't write this stuff. I'm going, yes, they can. It's not magic. It's hard, but it's not impossible. Option number 2 is you can use a canned application. And this is a good way to get started. This is a snapshot of an old version of a tool called Weka, W-E-K-A. It's a sort of WinForm-like application written in Java. Excuse me. But it's a good way to get started. It's an open source thing. You can download it onto your machine and play around with it and get up to speed. And there's a lot of sort of examples on the net. Then the third approach is that there are commercial or open source API sets to implement neural networks. Now everybody's different, but I don't like this approach because whenever I learn some new API set, it takes me twice as long as if I just learn how to do it myself. But that's just me. And then they're constantly changing it. And you ever try to like learn something on CodePlex or something like that? You start looking at the source code and you forget it. I give up. But those things are out there. You can buy them or get open source ones. So that's a third approach. Depending on your background, you might want to go that route. Now, here's the vision for the future. I actually made this slide years and years ago, where this is an approach that will be available to you, I promise, sooner rather than later. There's going to be a surface that resembles kind of like Visual Studio. Visual Studio is a great thing, especially for the drag and drop controls and stuff like that. So you imagine kind of like a neural network toolbox where you have all of these little components, and they're just code, but you can drag them onto your design surface and then you can connect them. So it might look for that iris thing. You would have an iris data reader thing, okay? And then iris table, that would be something that puts it into a matrix in memory. Then you'd have something that would break it down to train tests. And all this stuff would either be written by you could code it up yourself for custom purposes, or you could get a bunch of experts, who have their own tricky algorithms. So, and here we have like the neural network classifier sort of down the left. It's selected, and then something selected would give you context, and you supply information, which is, fields and properties and stuff like that. So, trust me that this vision will be available to you sooner rather than later, but that's all I can say about it. This was the Cortina demo by Cortina. Here's the resources for you, and of course this will be posted on the Build website, so you don't have to write it down. But this first one is the concepts. For me, if you want to know about neural networks, this link is the authoritative source about all information. Everything you need to know about neural networks is there, and it's all accurate, okay? For the most part. There's only like a few things. A lot of the stuff out there, especially on Wikipedia, I love Wikipedia for a lot of things, but Wikipedia for neural networks is a disaster. Do not go there. Weka, there's the link to that tool. I created on a special external site the custom C# code. That iris data is right there, and you just go in. It's a web page. You just copy it and paste it into Visual Studio, and you're good to go. It'll run. No files. Don't you hate it when there's something extra files or this that one file? The speech demo, same thing. You can get that from there. That's it. I'll encourage you to fill out the things, and there's always this awkward thing. I'm going to take sort of questions. I'm not going to do the questions sort of like on the microphone and stuff like that. I'm going to turn the microphone off and ask you to come up here. If you have any questions, we'll try to answer as much as we have for the next couple minutes before we get kicked out. For the rest of you, go away, shoo, and go enjoy that great lunch coming up.